Hey everyone, welcome back, and let's write some more neat code today. So today let's solve the problem, painting the walls. We're given two arrays, cost and time. They're both going to be the same size in this case, n. So I'll blow them up here. And we're also given a story, and with hard problems, it's all about how you interpret the story. So they basically tell us we're given two painters, and these two arrays represent the cost of painting each wall. So in this case, let's say we have 4 values in each array. That means we have 4 walls. And for the first wall, it takes this much. This is the cost it takes to paint that wall, and this is the time it takes to paint that wall. And the same for all of these others as well. Now, the first painter we have is a paid painter. For them to paint this wall, it's going to cost them this much, and it's going to take them this much time. And we also have a free painter who can paint any of these walls in just 1 unit of time. And it also doesn't cost them anything to paint that wall. So this is a pretty good painter. The catch though, and the way they phrase this, you really have to pay attention to it, is the free painter can only be used if the paid painter is occupied. So of course they're going to word it in a way that's not the most simple, but it's pretty easy to understand what they mean here. Like basically the paid painter, whether they're painting this wall or this wall or this wall, let's say it's this wall, it takes them 3 units of time to paint this wall, and it costs them 3. So in that time, only then can we have the free painter maybe paint this wall and this wall. We could also have the free painter paint literally all 3 of these, and the reason is because it takes them 1 unit of time for each. We can ignore the time here because the free painter can do all 3 in 3 units of time, and conveniently it took the paid painter 3 units of time to paint this one. Now if we had the paid painter paint this wall, there's only 2 units of time for the paid painter to paint this one, so the free painter could maybe get to this one and get to this one, but they could not get to that one, so the paid painter would have to do that one. And they also don't really mention in what order the walls have to be painted. So that's for us to decide. But if you're clever, the most important thing to notice about this problem here is that we only need to keep track of what the paid painter does, because even in that first very simple example I showed you, we can technically start from any of these, but probably we can start from the left and work our way to the right. And for each of these walls, we can decide which wall is the paid painter going to paint and which wall are they not going to paint. And the goal of this problem is for us to minimize the amount of money to paint all of the walls. We know the free painter doesn't cost anything, so for us to calculate the amount of money, really we just have to keep track of the paid painter, because what they don't do, whatever they happen to skip, is going to be taken by the free painter. And the last thing is this whole idea of the paid painter has to be occupied. Well, we can forget about that definition and we can think about it in a different way. We can think about it in such a way that for whatever walls that the paid painter paints, let's say it's these 2, and let's say we decided to skip these 2, for whatever we end up deciding on, the sum of the time of the paid painter has to be greater than or equal to the number of walls that we ended up skipping. So in this case, it's 2. So this has to be greater than or equal to 2, whatever the walls remaining were. It's not like this is insanely complicated. Just going through a few examples, this is an observation you can make. It might not be the first thing that you're looking for, but just going through some examples, it's kind of obvious, isn't it? That's kind of where the equilibrium lies. Because we know if it takes 3 units of time for us to paint these, then basically the paid painter is occupied, of course, for that time. It doesn't matter what order we do these in. And it doesn't even matter what the cost or the time of the walls that we skipped happen to be, because the free painter can do them in 1 unit of time and 0 cost. So that's what we're looking to do. And once you kind of realize that, thinking about this problem recursively becomes pretty easy. For each wall, we can decide to include it or skip it. I'm going to basically assume you know like what a decision tree is. So as we do this, we're going to be iterating through the array. We're going to need a pointer I, which tells us like which index we're at in the array. So that's one variable for our recursion. We know, of course, like here, we're going to start at index 0 and then like work our way through the array. And I talked about we need to keep track of what the total time we have for the paid painter. For all the walls that we actually choose, we have to keep track of what that is. Initially, maybe that can be 0. And lastly, we have to keep track of how many walls are remaining. That should be pretty easy to keep track of, shouldn't it? Because initially we start with n walls. Every time we actually choose a wall to paint, we can take n and decrement it by 1. Initially, it kind of seems like we need 3 variables, and I will say that this is probably the part that makes this a hard problem. We can take these 3 variables and actually condense them into 2 variables. Let me show you how we're going to do that. First of all, recall that I said that the sum of like the total time has to be greater than or equal to what we have remaining, like the number of walls we have remaining. Well, we can do a little bit of algebra, a little bit of math on this equation, subtract the time from both sides, and we can rearrange this inequality to be 0 is less than the amount remaining minus the time. So in other words, we can just have a single variable. Like this is kind of the big jump. This is probably the part that you might repeat if you're watching this video, so I'll try to go slow. We don't need to keep track of both the time and what we have remaining. We can condense that into a single variable. I'm going to call it remaining because that's what it represents. It represents the number of walls we have remaining. Like if I decided that the paid painter is going to paint this wall. We started with 4 walls, didn't we? I'm doing the math on this side. We started with 4 walls. So I'm definitely going to subtract 1 because we literally just painted a wall. We have 3 walls left. So I'm definitely subtracting 1 every time we paint a wall. So that's pretty simple. That's just remain so far, right? We're just counting the remaining walls. But in the time that the paid painter painted this wall, there was 1 unit of time. In that time, we know that the free painter can paint any of these. We don't necessarily care which one, but we know they're going to paint one of those. So we're not only going to say 4 minus 1, we're also going to subtract the time at that index, which is also 1. That's kind of what we're doing. That's what remain is representing. It's representing the remaining walls. And this kind of equation here is a little bit of the intuition of why we're doing that, why we're subtracting the time from that as well. We're kind of accumulating the time for the walls that we select. And as we aggregate those, we're subtracting them from what we initially started with remaining, which was like the length of the arrays, because that kind of tells us how many walls we started with. So I'll kind of do a quick example. I'm not going to go through this entire tree, but just to give you a bit of the intuition of what we're doing. Initially, we are going to start at 0. N is going to be 4 in this case. I'll use a different color. And if we go left, we're choosing this wall. So we're going to be at index 1, and what we had remaining is going to be 4 minus 1 because we chose a wall, and minus the time, so it's going to end up being 2. If we skip this, then we're going to be at index 1, but we skipped the wall, so we still have 4 walls remaining, so this will stay as 4. If we go down now this branch, we're going to be here. We can choose to paint that wall or skip it. If we paint this wall, then, well, first of all, we're at index 2, and we will take 2, which is how many walls we had remaining, and subtract from it 1, and subtract from it the time it took to paint that wall, which is another minus 2. So now we're going to be at -1. We have -1 remaining. That means we probably painted all of the walls, right? So that's kind of our base case. Anytime that the remain count is less than or equal to 0, we are done. That's one base case. The other base case is if we probably reached like our I pointer all the way out of bounds, but the remain count is still greater than 0. In that case, we have a base case as well, but we're going to handle that a little bit differently because we didn't arrive at a solution. But that's kind of the main intuition of this problem. The fact that we were able to condense this into two variables, I and remain, means we can add memoization and do so a lot more efficiently than if we had three variables. That's going to make this solution big O of n squared, because I is going to possibly iterate through the entire array. Remain is initially going to be the same size as the input array. So that's the time complexity. That's also going to be the memory complexity, because that's like our solution space with a memoization. So now let's code this up. Okay, so I'm going to write out the recursive function. I usually call it DFS, and the two variables we talked about, I and remain. And I'm actually just going to pass those in as I call DFS down here. We know we're starting at index 0, and initially remain is going to be the number of walls we have. So we can take either the length of cost or the length of time. And we mentioned that the main base case here is going to be if remain is less than or equal to 0. In that case, we're going to return 0. The other base case, and I'm going to change this, but for now, we're going to say if I is out of bounds, if it's equal to the length, we're going to return a default value. We did not find a solution, so we probably don't want to return 0. We're going to return a very large value, infinity, so that we don't act like we had a solution when this is returned. But we're returning 0 here because we painted all of the walls. And the subproblem here is basically we have no walls to paint, in which case it costs us 0 to paint 0 walls. That's the logic, at least, and that's what we're going to assume when we actually make the decision here. We're making two decisions. We're either painting the wall. If we paint the wall, what is the cost of doing that? It's going to be, first of all, the cost of the ith wall. That's pretty straightforward. And the cost of painting, the rest of the walls, or at least minimizing the cost from painting the rest of the walls. Well, the simple thing here is we're going to start at I plus 1. The other thing is, what's remain going to be? If we painted a wall, remain is not going to stay the same. If we paint a wall, we always subtract by 1 because we just have one less wall remaining. But also, in the time that it takes to paint that wall, let's say it was 1 unit of time, well, then the free painter is going to paint 1 wall. If this was 2 units of time, the free painter is going to paint 2 walls. So we should always take this and subtract it from whatever remain happens to be. So that's the intuition. Add these up together, we get the total cost it took to paint the walls. Now, if we skip this wall, we are not going to add cost of I, so we don't have to do that. And we are still going to call DFS and start at I plus 1, but remain in this case is going to stay the same. If we don't paint a wall with the paid painter, then the free painter can't paint anything either, so this is going to stay the same. Now, what are we going to return from here? Probably the minimum of both of these. That's what we're trying to do here anyway. We're trying to minimize the result. So this is the brute force solution. So now we're going to add memoization to this, and I usually do that with a hash map, so I'm going to declare that up here. And I actually realized I can't do what I was about to do. I was going to kind of condense this into the cache, but I realized we have 2 parameters, so I can't do that. I would need to account for every combination where I is equal to length, and we could have multiple values for remain. So what I'll do here, though, is we know if we ever see this combination of parameters a second time, that we don't have to run through the recursive case. So that's what I'm adding here. I remain is in DP, then return whatever value we happened to cache here. But if it's not, then compute it and then throw it in the cache just like this, and then return it after we have cached it. And so that's pretty much the optimization that we make. The fact that we have 2 parameters is what makes this efficient. So now let's run this to make sure that it works. And as you can see, yes, it does. And even though like the big O time complexity of this is as efficient as we can get, it doesn't look like it's super efficient. And that's probably because if we were to just add the cache decorator here, I think that usually speeds it up because Python's interpreter is written in C, and this decorator, I think, will be executed in C rather than like interpreting the lines of code that we actually wrote, which is generally slower. If you found this helpful, please like and subscribe. If you're preparing for coding interviews, check out Leetcode.io. Thanks for watching, and I'll see you soon.